we're going to be looking at the energy conversion taking place in simple harmonic motion. When a system oscillates with simple harmonic motion, there's a continual exchange of energy between kinetic energy and potential energy. So kinetic energy will be maximum in an oscillation when the velocity is maximum, so that is at the equilibrium position. Kinetic energy will be zero when the velocity is zero, so that is at maximum displacement, so when displacement equals the amplitude of the oscillation. Because of the continual exchange between kinetic energy and potential energy will be maximum when kinetic energy is zero, so that is at maximum displacement. And potential energy will be zero when kinetic energy is maximum, so that is at zero displacement, that is when the oscillation is at the equilibrium position. So we know from principle of conservation of energy that the total energy in that system will remain constant, and if we assume that there's no wasted energy due to friction, then we can say the total energy will equal our kinetic energy plus our potential energy. So when our potential energy is zero, that means the kinetic energy will be maximum, and that will be our total energy in the oscillation. We know kinetic energy equals a half mv squared, so our total energy will equal a half v max, the maximum velocity, squared. In simple harmonic motion, the maximum velocity is equal to the angular frequency omega times by the amplitude a. So if we was to substitute for v max into the equation for energy total, we would get energy total equals a half m times our v max squared, and our v max is the omega a all squared. As mass m and angular frequency omega are constants for a particular oscillation, then we can say the total energy is directly proportional to the amplitude squared. So if we were to double the amplitude in an oscillation, then the total energy would quadruple, because you've increased the factor by 2 squared. If we was to plot a graph of the energy against the displacement, we would get these three lines. The red line is showing you that energy is maximum when displacement is zero, that is at the equilibrium position, and the energy is zero at maximum displacement. So that's telling us the red line represents our kinetic energy. For the blue line, you can see it's zero when displacement is zero, but it's maximum when displacement is maximum, so that represents our potential energy. And at any displacement, if we was to add our kinetic energy with our potential energy, we'll get our total energy, which is represented by the green line. So you can see that when the potential energy is zero, kinetic energy is maximum and is equal to our total energy. So if we now consider the energy transformation taking place for a pendulum, positions 1 and 3 represent maximum displacement, and position 2 represents zero displacement, that is the equilibrium position. At maximum displacement, we know velocity is zero, so that means the kinetic energy will be zero and the potential energy will be maximum. At zero displacement, we know velocity is maximum, so therefore kinetic energy will be maximum, and so potential energy will be minimum. Here we have a velocity time graph for an oscillation undergoing simple harmonic motion. To get a kinetic energy versus time graph, we know kinetic energy is proportional to velocity squared. So at any given time t, we will square the velocity, and so that will give us this graph. It's important to note that we do not have negative kinetic energy. So when the velocity is negative, when you square it, you get a positive value. So you can see when velocity is maximum, kinetic energy is maximum, and when the time when velocity is zero, kinetic energy is zero. So the velocity time graph is following a cosine shape. So the kinetic energy time graph is showing a cos squared shape. To get the potential energy versus time graph, because we know there's a continual exchange between kinetic energy and potential energy, so when kinetic energy is maximum, kinetic energy will be minimum or zero. When kinetic energy is zero, potential energy will be maximum. So the potential energy time graph is the reverse of the kinetic energy time graph and follows a sine squared shape. So the kinetic energy time graph is following a cosine squared shape, and the potential energy time graph is following a sine squared shape. So if we was to add our kinetic energy and potential energy at any given time, as you know, a cos squared plus a sine squared will equal 1. So that will give us the total energy being constant throughout at any given time.